Good day to all. Now we are going to see about the comparison of this synchronous motor with the induction motor. See, for a given frequency, the synchronous motor runs at a constant average speed. Whatever the load is there, while the speed of induction motor falls somewhat with increase in the load. The synchronous motor can be operated over a wide range of power factors, both lagging and leading. But induction motor always run with the lagging power factor, which may become a very low in light loads. Whereas in that synchronous motor have a wide range of power factor. Then the synchronous motor inherently not self-starting, but induction motor is a self-starting one. Here it is not a self-starting, but in that induction motor is a self-starting one. Then the changes in applied voltage do not affect the synchronous motor torque as much as they can affect in the induction motor. In that induction motor it will affect the torque, but here it is won't affect the torque. Then the breakdown torque of a synchronous motor varies approximately as the first power of the applied voltage, whereas that of an induction motor depends on the square of this voltage. Then DC excitation is required to be a synchronous motor, but not by the induction motor. Then this synchronous motor are usually more costly and complicated than the induction motors, but they are particularly attractive for low speed drives, which is below 300 rpm, because their power factor can also be adjusted to 1.0 and their efficiency is high. However, induction motors are excellent for a speed over 600 rpm. Then the synchronous motor can be run at ultra low speeds by using high power electronics, which generate a very low frequency. Such motor of 10 millivolt range are used for driving a crusher and a rotary kilns and variable speed balls, mills, etc. Now we will move up to that synchronous motor applications. What are the synchronous motor applications are there? See, synchronous motor find extensive application for following classes of service. First one is power factor correction, then a constant speed, then constant load drive, and the third one is voltage regulations. The synchronous motors have the following fields of applications, which is in powerhouses and substations. In that powerhouses and substation, which is used in parallel to the bus bar to improve the power factor. Then in that factories, use in the factories having a large of induction motors or other power apparatus are operating a lagging power factor to improve the power factor. Then mills, industries, etc. Used in textile mills, rubber mills, and other big industries, cement factories for power applications. Then constant speed equipments used to drive continuously operated and a constant speed equipment such as fans, blowers, centrifugal pumps, and motor generator sets and air compressor, etc. Now the power factor correction in that motor. See, it has been that a synchronous motor can be operated in both lagging and leading power factor by varying the field flux excitation circuit. On overexcited back EMF EB is greater than the supply voltage, motor can run with the leading power factor. The condition of that leading power factor, the back EMF EB should be greater than the supply voltage. Then it will become a leading power factor. When a synchronous motor operates a leading power factor, the behavior of it's like a capacitor or condenser. That's why a synchronous motor operating a leading power factor is referred a synchronous capacitor or synchronous condenser. We can say if the synchronous motor is in a leading power factor, then also we can say that is the leading capacitor or a leading condenser. Thus, overexcited synchronous motor leading power factor are widely used to improving a power factor by supplying a leading reactive power. Of those power systems which employ a large number of induction motor and other devices having a lagging power factor. A constant speed and constant load drives. Because of their high efficiency and high speed, synchronous motors above 600 rpm are well suited for loads where constant speed is required, such as centrifugal pumps, belt-driven reciprocating compressors, blowers, line shafts, rubbers and paper mills, etc. Then these low-speed synchronous motors below 300 rpm are used for drive such as centrifugal and screw type pumps, balls and tube mills, vacuum pumps, chipper and metal rolling mills like that. Then that voltage regulations. See here when the voltage at the end of along transmission lines is varies greatly, especially when large inductive load are present. See this voltage at the end of transmission line varies more. It can vary more when the large inductive load are present over here. But when an inductive load is disconnected suddenly, the voltage tends to rise considerably above its normal value because of this line capacitance. By installing this synchronous motor with the field regulator for varying its excitation, this voltage rise can be controlled. When the line voltage is decreases due to inductive load, the motor excitation is increased, thereby raising its power factor, which compensates for the line drop. If, on the other hand, line voltage rise due to line capacitive effect, more excitation is decreased, thereby making its power factor lagging, which helps to maintain a voltage is a normal value. See here, if the other hand line voltage rise, if the line voltage rise due to line capacity effect, then the more excitation is decreased, thereby making its power factor lagging, which helps to maintain a line voltage. So we have to maintain a power factor lagging, for that maintain the line voltage as it is in that normal value. Then you can see here that voltage regulation, it has that installing of synchronous motor with the field regulator. This is a voltage rise can be controlled over here, but if you are seeing here, it won't be in maintaining the line voltage because of this low power factor lagging. So in order to avoid this low power factor, for that maintaining the line voltage, what we'll do, we have to decrease this power factor lagging. For that, we'll have motor excitation should be decreased. If the motor excitation is decreased, then we will have a low power factor, which means this power factor will be used to maintain the line voltage as it is in the normal value. That's all. Thank you.